So let's start the session of this. And so the speaker is Professor Rudy Rucker, and from San Jose State University, but maybe so science fiction writer is more, yeah, I know from that. But, okay, so.
Thank you. It's nice to be here. I haven't been in Japan for about 10 or 15 years. It's nice to be here again, and this has been an interesting conference. Actually, that rule up there, Kaneko-san, that's one of your rules. That's toroidal coupled lattice, yeah, with the logistic map running in each cell. But, so I was excited to find you here. These pictures are from some software called Kapow that I wrote at San Jose State, and you can get the software for free online. You can, basically if you go to my website, rudyrucker.com, you can find links for all the things that I mentioned here. And this is based on continuous valued cellular automata. And today I'm going to talk, I draw a lot of my inspiration from cellular automata. I got into computers in the 1980s when I moved to Silicon Valley. Until then I was a mathematician, and then I had a chance to switch over to computer science, and this particularly cellular automata interested me because these are these small computational worlds where we have things very much, these are in many ways sort of like embryos, and they emerge spontaneously. If I randomize the screen, these things will come back. So I'm going to talk a little bit about cellular automata. But now let's switch to the PowerPoints for my talk. And let's see. Wait for it to come up. My computer's a little slow today. There. Let's see. Slideshow. Is there some shortcut key? Does somebody know the shortcut key? Start slideshow? That might work.
At the bottom? Yeah, okay.
Oh yeah, there we go.
Yeah, right there.
That one, right? That's it. That's the end of the talk. Okay. Oh, there we go. There we go. So life is a gnarly computation. That's the theme I'm going to talk about. And I use gnarly in a special sense. It's what, one thing about this conference, it reminds me in the 1980s, I went to a series of conferences on artificial life that were held in Santa Fe and Los Alamos. And Christopher Langton was the sort of organizer. And it seems there's some of the same enthusiasm here that there was at those conferences. But it's the 21st century, and the level of biological work in particular is so much higher than anything that we had in the 1980s. It's amazing to me how much biotech has advanced. Pretty much all we had in the 80s was computer simulations. But, okay, and the reason I mentioned Langton is because he uses the word the edge of chaos, and he talks about life as emerging at the edge of chaos. And I prefer a more California word for that, so that's why I use the word gnarly. Okay, now let's, the idea that I'm pushing these days, I tend to every few years adopt a new idea about the universe and try to convince myself that it's true. The Cubist painter Picabia said, ideas are like shirts. I like to get a fresh one every day. So the idea that I'm into these days is hylozoism. Now this, Florian can tell you, this is a real word in the history of philosophy. You can find it in Wikipedia. And it comes from hyle, matter, zoe, life. And so the idea is, what is life? Everything. Everything is alive. And it's not sort of the pantheist notion of the universe being alive, although that would be the case as well, but it's saying that each individual particular thing is alive. This handkerchief is alive, that screen is alive, the air currents are alive, the atoms in the room are alive, the galaxy is alive. Everything is alive. Now, that's not a popular notion. It was popular on and off in the history of philosophy a number of times. And also the word panpsychism is sometimes used for the same concept. Slightly different meaning, but very similar. There's a good recent history of panpsychism from MIT Press. One of the motivations for hylozoism, Gustav Fechner, a German philosopher in the 1800s, he said, the way we usually think of life or consciousness is that there's a few sort of bright sparks of consciousness and life, and the rest of the world is dark. So it's like this dark nighttime universe, and there's some sparks of light, we're like lightning bugs. And he said, why not believe in a daytime universe where everything is alive, and we're not the only thing that's alive. Lots of living things all around us. And it makes for a more congenial universe. And I myself have recently, when I take an idea like this, which sort of flies in the face of what the average person believes, then I like to develop the idea. And the technique I've used throughout my career, I've worked on 2 tracks, as a scientist and as a novelist. And what I like to do is take an idea that I'm interested in science and then write a novel about it. And the novel serves as a laboratory for a thought experiment. Because only in a novel do you have to have the sustained imaginative force to create a whole world and tease out the details of what might actually emerge if you say, let's change something. So I'm actually currently writing a novel called Hylozoic, about a world in which everything has become alive. And to play fair by the rules, I am a computer scientist and a mathematician, so I have a sort of an explanation of how everything becomes alive in this universe. And I'll talk a little bit about that today. Now, one other thing, it seemed like I should mention something Japanese since I'm here. And is a fluttering flag alive? And that goes back to a well-known koan where the monks are looking at the flag and they're arguing. And one of them says, the flag is moving. And the other one says, no, the wind is moving. And then someone else says, mind is moving. And that's, I always liked that koan very much. And so a notion, I'm going to use the flag as my guinea pig for hylozoism. Is a fluttering flag alive? So that's the question we're going to wonder about. The method I like to use is dialectical. I like to brag. Georg Hegel was my great-great-great-grandfather. And some of the ideas for this talk are from a nonfiction book I wrote that has a dialectic title. And the book's title is The Life Box, the Seashell, and the Soul. This is the last nonfiction book I wrote. I wrote it, I retired from teaching at San Jose State. I taught computer science there for 20 years. And I went through a lot of different computer languages during the years, and I worked as a programmer at Autodesk for a while. So I got quite familiar with computers. It was Silicon Valley, the big wave was coming up. It was an exciting period in my life. And then I wanted to think, well, what have we been doing all this years? What have we learned? What is computer science about? And it occurred to me, just as there's a philosophy of mathematics, there should be a philosophy of computer science, which there are a very few volumes that treat this. It's sort of a new subject. You could even call it early geek science, or early geek philosophy, instead of early Greek philosophy. But anyway, so that's, I mentioned dialectic, and I'm going to return to dialectic a few times. So the title is dialectic. So why is that dialectic? Well, first I have to tell you what the word lifebox means. And I made the word up, so don't be ashamed if you don't know what it means. But for the moment, let me just sketch out what I mean by the triad. Lifebox is the thesis, soul is the antithesis, the synthesis, and sometimes I think of synthesis as an escape. You get into an irresolvable contradiction, and you're stuck, and then you fly out, you move up to a higher level. So that's synthesis or escape. And the escape is the seashell. Now, what exactly am I getting at with those three words? Well, I'll make that clear now. First, one more picture before I talk about it. The life box is the idea, that's the thesis. It's the idea that we are computations. There's a notion that I call universal automatism. And here I've fallen under the thrall of Stephen Wolfram. Stephen Wolfram's book, A New Kind of Science, had a tremendous effect on me. Actually, Wolfram himself had a tremendous effect on me, because I met Wolfram in 1982, and at that time I was an unemployed freelance writer, and I saw some pictures of cellular automata in Scientific American, and just something about them really appealed to me. And so I went and found Wolfram at the Institute for Advanced Study and interviewed him, and he basically converted me on the spot. And I thought there would be more converts, actually. But his work is not as popular as I think it should be. But anyway, he believes universal automatism, everything is a computation. So that's one view of the world. The opposing view of the world is, look, I know that I'm not a computation. I'm not a cell phone. I have a soul, I have dreams, I have intentionality. Obviously, everything is not a computation. Computers are boring, they're dull, they're not robust, they break. That's not what a living being is like. That's the antithesis. The synthesis is the seashell. Now, why is that seashell the synthesis? Well, this is again something that Wolfram got into. This is the cone shell that lives in the South Pacific and Micronesia. It has this pattern on it, that's a cellular automaton. And the pattern is generated by the lip of the cone shell, where it has this growing edge, and it has pigments that are in this lip. And the lip basically functions as a one-dimensional cellular automaton with patterns moving up and down it. And what you have on the shells outside is a space-time trail of a one-dimensional cellular automaton. And the significance of this pattern is that on the one hand, it's deterministic. It's a computation. Those rules I was showing you right before the talk, those colorful things going on, those are all completely deterministic. You'd start them over with the same seed, and the same thing would happen again. They're computations. But they look fluid and living. They look strange. And so the synthesis is the idea that we can have gnarly computation. And if you have, and by gnarly computation, I mean a computation that looks living, looks complex. What's still sinking in is the notion that computations don't have to be dry and dull. So that is the synthesis that I'm proposing between these three things. So again, going over what I just said, the thesis, universal automatism, the world is made of computations. Now, just as defining information is an important thing to do, defining a computation, I say it's a process that obeys finitely describable rules. And this is a fairly minimal definition because I want to go and say that everything's a computation, so I don't want to be too restrictive. I do want to say the rules are finitely describable because otherwise everything would be tautological. Everything would obey the rule of being like itself. Now, another point, the world consists of many computations at high and low levels. There does not have to be a single underlying computation that generates the whole world. I mean, it's possible that's true as well, but that's a much stronger claim. I think Wolfram believes this. Okay, he has a dream of finding the one true rule. But I think it's, at least in this stage of the history of philosophy of computer science, it is more reasonable to just satisfy yourself with saying there's many computations. Now, in my book, The Life Box, the Seashell, and the Soul, I actually have 7 chapters. In one chapter, viewing physics as a computation, viewing biology as a computation, viewing society as a computation, viewing philosophy as computations. So it's a series of levels that it works up through. Finally, the word life box, the idea is if we think of human mind as being a computation, then another word that I like to use for the human mind as a computation is life box. And I'm kind of interested in this from a science fictional point of view. One of the dreams in cyberpunk science fiction that I was involved with in the 1980s was the idea that we can upload our minds into the web, or I can copy my mind into a robot. Like, it's something, by now it's somewhat of a commonplace idea. When I first started writing about it in 1980, it was a very strange idea. It was not an obvious idea. The novel I wrote about was called Software, actually. Most people didn't know what the word software meant. And so I had these robots who came and ate this man's brain, and was cyberpunk. And then they get out the software from the brain, and then they load it onto a computer, and they have a robot copy of the man. And to some extent, we're trying to do this all the time nowadays. When you have a website that has a huge amount of information about yourself, you're sort of making a software model of yourself. That's one of the motivations. If you're a blogger, if you like blogging and putting all your pictures online, putting videos online, sounds, you're creating a sort of simulacrum of yourself. Now, at this point, when you create this software simulacrum of yourself, we still don't have very good artificial intelligence software. It's sort of shocking, the state of artificial intelligence. I taught artificial intelligence for a number of years, and it's just a bunch of cheap tricks. There's no theory, there's nothing there. It's incredible how weak it is. We always dream though, maybe in 10 years, it's always in 10 years, we're gonna have, and there are some promising developments. I think one thing that's happening, people are getting a better idea of how the brain works. I think some of the things you all have been talking about here, very suggestive, the different layers we can look at. And in the end, probably any software that's AI-like will have to be evolved. After all, that's how we got our software, our brainware, millions of years of evolution. In any case, you can get a crude model of you and mine with a blog and a simple search engine. If you manage to write down everything that you ever said to anyone, then you could use that database to make a pretty good simulacrum of talking to you. You would simply look up times when people had prompted you with similar questions and regurgitate the answers. In any case, antithesis, life doesn't feel like a computation. There's the feeling of being alive. That's the sort of core thing that we all have. I am, this sort of irreducible sense of existence, this feeling that there's this light inside you, that there's something going on. Another sense of consciousness as merging with the world, where you feel like you entangle yourself with the world, you flow out of yourself and have empathy with things. Dreams, visions of God, in short, the soul. These are the things that seem not to be like a computer. Now the synthesis is, as I say, gnarly computations are lifelike. And by gnarly, I mean complex and unpredictable. And I'll say a little bit more about that in just a minute. So, reprising one more time, thesis, living things are computations, and applying it now to life. Living things don't seem like computations. Synthesis, living things are gnarly computations. And that's the theme that I'm getting at. Now we may be, is it enough to be a gnarly computation to be alive? Do you need more? I'll get to that a little bit later as well. But for now, this is where I'm headed. Okay? I'm saying we can say everything's a computation. Computations don't seem living. But once if you hang around with computers enough, you discover there are these things called gnarly computations. And here's another picture. This is a cone shell. These are very interesting creatures, by the way. My last book, Mathematicians in Love, I had some alien cone shells. They're about this big, and they can fly. They're very nasty creatures. It turns out they can shoot out a harpoon. They have this detachable tooth. They shoot it out on a strand. It has this incredibly powerful drug in it. It's called a conotoxin. And recently some people patented conotoxins for use in removing pain that you can't get rid of. But it's such a strong drug that they have to drip it directly into your spinal fluid. Otherwise you get convulsions. And usually when they give it to you, eventually you have to stop because you have hallucinations and have to be put in a straitjacket. It's not exactly a party drug, conotoxins. So he shoots the fish with the conotoxin, then he gets his mouth out, pulls it inside the shell, and then deposits this bag of bones that's wrapped in slime. Clearly, you can see why I would want to put them in a science fiction novel. Okay, so anyway, but the point of this thing is the pattern he has. Now let's talk a little bit about the spectrum. This is the complexity spectrum that we've been looking at for many years. We have there's sort of four classes of cellular automata. There's rules that are simple, they die out, rules that repeat, rules that are lifelike, rules that are sort of pseudo-random. And if you like, you can think of it as sort of, these rules are too cold, these rules are too hot, these ones are just right. They're the gnarly rules. So the simple rules have a repeat. The gnarly are complex, moving, and unpredictable. Let me maybe show you some cellular automata for a second, if I can. Let's see here. Let's come back to this thing, and let me load a simpler pattern. Let's load it for CA classes. Okay. Now this is examples of the four kinds of cellular automata. Now let me do this also. This is the one that essentially tends to die out or repeat. Let me do this. Let me reseed it. So now I'm looking at it, I can't tell which one is which kind. That's actually a real problem with cellular automata. But so let's do all of them. Let's randomize all of them and see what happens. Oh yeah. See that one, see the upper left one, that's one that dies out. So I'm starting it with a fresh line, okay? And then the interesting stuff is dying out. So this is space, and this is time. These are four different little worlds, okay? We're scrolling up. And so if I give it one seed, this is maybe easier to see here. This is one that's doing something, it's sort of dead, nothing's happening at all. This one is doing something that's repeating. Now it looks like it's doing more than repeating because it's wrapping around and folding over. This one is basically seething dog barf. You can use this for a randomizer, okay? In fact, Wolfram patented this rule for using as a randomizer. And actually, when I was at Autodesk, I wrote a shift register randomizer that was based on that rule. This is rule 30, and this is rule, I think this is rule 110. And so seeking them again a little more, it's, so you notice this one, it basically looks like beer foam. You've got randomness. It's sort of not interesting. This other one, although it looks interesting, it's only interesting because I gave it a random seed. If I give it something simple, nothing happens. Let's look at this one a little bit bigger. Let's look at this guy, give him one seed. Let's take up the whole screen. Okay. Notice this part is orderly, but what you're getting here is essentially complete pseudo-randomness. Now, this is deterministic. It'll do the same thing every time. This is a good example of a cellular automaton that's it's unpredictable. It would be one of the things about cellular automata. If I say, well, suppose I run this for a half hour and then stop, is this pixel here going to be black or white? And there's no algorithm. There's no shortcut to figuring that out. You say, I just have to run the cellular automaton for an hour. It's not a compressible computation. It's irreducible. It's not predictable. Now, this rule, though, is not very interesting because it's not gnarly. So let's look at this rule. This guy is, this is sort of the star. This is rule 110. And Wolfram proved that this rule actually is computation universal. You can take, you can emulate any possible computation with this thing by giving it the proper start line. And what you have is these gliders moving back and forth, and they're moving information up and down on the line. Again, the rule for this, when I call it Rule 110, that's because the whole code for the rule, the whole program, is the number 110. If you write it out in binary, it's 8 bits, zeros and ones, and it has this 8-bit lookup table. Each cell looks at its left neighbor, itself, and its center neighbor. And there's actually 8 kinds of neighborhoods you can have. 0, 0, 0, up to 1, 1, 1. Yeah, so these are the kinds of computation that interest me. These are gnarly computations. And if you take any class of computations, like Turing machines or anything that you like, even biological computations, network computations, you'll sort of always find these 4 classes. The rules that die out and reach an equilibrium. Sometimes that's good. If you want something to like compute some number for you, you want it to just compute the number and stop. You don't want to go on forever. But if you want something that's like a living organism, that's not going to do it for you. So there's the rules that die out. There's the rules that repeat. There's the rules that seed. And then there's these kinds of things where we have structures keep moving around and doing interesting stuff. And this one is actually still alive, I think. Yeah, I think it's still going to keep doing stuff for a while. But now these rules aren't as interesting as they could be because they're one-dimensional. So that's why I prefer to look at, let's see. Well, let's just stick with the life is a gnarly computation. I like these kinds of rules. These are 2-dimensional rules. And what's going on here, well, gee, there's all sorts of things going on. Like this one here, this is the wave equation. So basically, if I just seed this thing, I could seed this guy with just a Fourier pattern. So I could put some smooth pattern in it. So basically, I'm just looking at a vibrating membrane here, and I could flip it over and flip it. Let's see, let's not do that. Let's do, yeah. So I can see you've actually got a membrane here. And then we can go back to the 2-dimensional view. And then, but this is actually a nonlinear wave equation. I put in a quadratic nonlinearity. So I can go, and if I damage the thing a little bit, I'll get, what's the word when a numerical simulation breaks down? There's some technical word for it. I can't think of what the word is. But it's a place where it's breaking down. It's interesting to look at what's happening in 3 dimensions there, but I better not get into that, or I won't have time to finish my slides. Okay, so you can play with this at home. So let's zoom back at it. Yeah, the ones that interest me, whoops, I changed everybody into that rule, so I better load this guy again. Life's a gnarly computation. Let's load that one again. Okay, there we go. Now, these are probably the most interesting ones, these kinds of rules, because you can start from a random start. Basically, I seed this with a random seed of zeros and ones, and I get these little fetuses emerging. And this, of course, many of you will know, these are called Belousov-Jabotinsky patterns. They were first created in the laboratory. And Arthur Winfrey investigated them a lot. I think he was the first one to do computer simulations of them. And Kaneko has worked with them as well. And these particular ones, Alan Turing, the father of computer science, was interested in creating patterns like this. And he had the idea of doing reaction diffusion systems. So this is actually modeling a chemical system where I have an activator chemical and an inhibitor chemical. They're both diffusing and they're reacting with each other in certain ways. And what we're seeing is the concentration of one of those two chemicals. Each cell here holds two real numbers. This is sort of a historical accident that cellular automata are usually just using a single bit per cell. It has to do with the fact that our computers used to be too slow to handle real numbers. Anyway, so this is again a little more taste of what I mean by gnarly computation. And the point is, again, this is not, I mean, if you say life is a computation, first you say, well, that can't be, computations are dead, they're dry. You see this kind of stuff, and you think, well, maybe they are computations. But of course, that's not news to most of you here, because you've been showing things like this all day. Okay, let's push a little further now. Let's see where we're headed. So gnarly 2D CAs, Kapow, Jabotinsky scrolls. Now, there's two things that come out from studying. Basically, these are sort of hypotheses or inductive conclusions, or perhaps we might call these abductive conclusions that I've drawn. And these have really come from Wolfram. The principle of computational equivalence is that nearly everything in nature is gnarly, okay? And something else related to that is, it turns out all gnarly computations, according to Wolfram, are in fact universal computations. It turns out it's not very hard for a computation to be universal. Universal means capable of emulating anything else. So we can observe that nature's full of gnarly computations. Most of these computations are in fact gnarly. Most of them are probably universal, that is, they can emulate anything at all. Principle of unpredictability, gnarly natural processes are unpredictable. And this is the kind of thing I mentioned where you can't say whether after an hour this pixel down here is going to be white or black. There's no shortcuts here. So these are, you can't actually simulate nature faster than the events occur. Now, gnarl is everywhere. So if I say, I used to just think that things like fire or air or water were gnarly because they're, you know, if I wave a handkerchief, it's doing something sort of interesting. Usually, one thing about a lot of our human-built environments, there's nothing, very little in this room that's visibly gnarly, except for us, the people, okay? But there's no plants, there's no water. If we could see the air currents, the room would look interesting. But it turns out even, I realized recently, even something like this is doing a computation. It looks like it's not doing anything, it looks boring. But if you go to the micro level, it's made up, it's a quantum computation, okay? It's a bunch of little particles connected with forces. They're sort of oscillating furiously. And even lower than that, rather than the rod and spring model, if you just take the quantum, view it as a quantum computation, it's doing exceedingly rich computations all the time. So really any object at all is capable of universal computation. So does that mean I can say that any object at all is alive? Well, if I want to go for hylozoism, that's what I want to say. I want to say every object is alive. But what else is needed? Surely life is more than just gnarly computation. Now, one possibility might be the missing part is memory. Now, the sort of salient thing about living organisms, the ones that we know, is that they remember. And there's three kinds of memory that we see. There's the genetic memory, the DNA. There's the organism's memory, the immune system. And then the behavioral memory, the neural patterns. So this is a sort of very slow learning memory, learns by evolution, takes, thousands of years. This learns in a matter of days or weeks. The immune system, over your life, your immune system is learning. This can learn, your neural patterns can learn very quickly. Now this is the sort of, if we come back now to the fluttering flag, the fluttering flag, certainly it's a gnarly computation. It's doing complex things. It's universal computation. It could compute anything. Is it alive? If I say life is a gnarly computation plus memory, does the flag have to remember its earlier states? Because it seems like it doesn't. So that seems like we're sort of missing out there. It seems like the flag can't be alive. So, okay, this comes back to, let's come back to that koan I mentioned. The flag is moving. The antithesis, the wind is moving. The synthesis, or escape, is the mind is moving. Okay? So, now can we apply this kind of mode of thought to the question of, is the flag alive or not? Well, let's see. Can the flag remember? Well, the thesis, the sort of natural thing to say is natural systems are dissipative. That is to say, there's different states converge. So you can't always retrodict what the past of things were. If you find something sitting on the floor, you don't know, did it roll in from here or from there? You can't really tell by looking at it. It doesn't have that memory. So natural systems don't remember. The antithesis, this is where the science fiction comes in. The universal memory upgrade adds memory to every point in space. I mentioned I'm writing a novel called Hylozoic, where I'm adding a memory upgrade. Because it seemed to me, as I say, I became convinced that unless I can give memory to objects, they probably won't be alive. So I had the idea of saying, well, the physicists, as a mathematician and as a science fiction writer, I like the fourth dimension. The fourth dimension is exciting. The physicists, the string theorists, they say, well, I'm going to take 12 dimensions. You say, well, that's cool. I like that. Let's have 12 dimensions. What are you going to do with them? Then they say, well, I'm going to curl them all up into circles the size of the Planck length, and I'm not going to use them for anything. It's like you won the lottery, and you're buying like putting your money in a mutual bond fund or something. Do something interesting with it. So in this novel I've been working on, I was thinking, how can I give memory to everything? So we'll take one of these dimensions that's being wasted, that the physicists, the stingy fools, are wasting. And we'll just snip it. We'll snip the 8th dimension. Instead of being a circle, we'll let it grow out to a line. And then you can use it for your memory. You can make marks on it. Okay? So every atom has its extra infinite universal RAM upgrade. So it can store its whole past. Every atom remembers its whole past. And then we could have the possibility. We've got the universal computation, the gnarly behavior, we've got the memory. So then everything can awaken. But of course this is science fiction. This probably isn't true. It probably is not true. Okay? Is there an escape? Well, if I want to say that the flag is alive and it needs a memory upgrade, but I'm not really going to unroll the 8th dimension, there's another move I could make. I could say the one mind already remembers for each object. So I could say the upgrade is in place. If I think of the universal mind that fills the universe as remembering what the past state of each object, that can serve as the memory for this thing. and the memory for this thing, and the memory for every atom. So I'm practicing believing that everything is alive, and it's a congenial view. Actually, in Japan, I notice all the signs I see, there's always pictures of living objects on the signs. Like at the trash can, the little pieces of trash have arms and legs, and they're talking to me. And I would walk by the graveyard, and there's an ad for a service to maintain your gravestones, and there's like a happy gravestone and a sad gravestone. So I think this is maybe a congenial viewpoint here, to think of everything as being alive. So, hylozoism. So I think that's pretty much what I wanted to say today. And so the book that I'm talking, there's actually two books that I'm talking about these days. That's the nonfiction book, The Life Proposition on the Soul, and this is the novel that where I'm starting to work up this hylozoism idea. And these, if you go to my website, you can always find them. And I have a blog where I put up a lot of stuff. Actually, I should take a picture of you all for the blog, so just give me a nice smile. Hi. Okay. Okay, so with that, maybe we'll stop and see if there's any questions. Very nice.
So, questions? Or
I'm confused by the memory.
Yes.
The memory is separable from the object. Can the object be alive, or is it just a representation of it in one moment?
So your question is, if the memory is separable from the object, is the what was
the object alive, or is it simply a representation of that object in one moment?
Oh, okay. That's a hard question. That's a hard question to start with. If the memory is separate from the object, if the memory is in the one mind, is the object just a representation of an aspect of the one mind? Maybe that's what you're saying. Yeah, well, maybe that's true. I like the idea of imagining, like when you drop something and it rolls under the bed and you can't find it, maybe it really doesn't want you to find it. Okay? Like the bean that gets out of the way. So I'm trying to imagine them actually having a kind of personalities. But yeah, there's a difficult point that you raise.
Yeah, a little semantic quibble, maybe you can get me out of it. To define something is to differentiate it from everything else. But if you define everything as alive, the word alive loses meaning because there's nothing that's dead. So I wonder how you get out of that.
Well, that's a traditional criticism of hylozoism, and I can't remember what the answer is. But I think I do have a little bit, there's a sense in which I know that I'm glossing over something important. Because obviously I know that really what a living being is, we think of it as something that learns and reproduces and is irritable and the usual sorts of things. And it does seem maybe a little bit a distinction without a difference. If I say that everything's alive, then am I saying anything at all? And perhaps at the logical level, maybe I'm not. But, well, two things. Maybe at the logical level I'm not, but at the emotive level, I'm saying something in that my attitude towards the world. If I'm saying every object is alive, it's going to affect the way that I feel about the world, and it will affect my behavior. And the other thing, this is sort of what I'm trying to do in this novel I'm writing now, Hylozoic. I'm trying to imagine a world where the objects actually were alive, and not just alive in the passive sense where I'm saying they're alive. They're alive in the sense they're actually talking to me. So there actually is a difference. Okay? If the objects were actually doing stuff and talking to me and interacting with me, then it would certainly be different from a place where they weren't. So there could be if we like go to a very extreme, we can imagine a world where hylozoism has real testable consequences. Yeah.
And while you've been talking, I just thought of a synthesis, an escape for you.
Okay.
And that is, you don't necessarily have to say that everything is alive, but you can say everything's alive or potentially alive. Because we're all made of stardust. Stars aren't alive in the usual sense until they pass through the pattern that we call life on the Earth. And so here you have this possibility, if you have a near infinite amount of time for the universe to sort of be alive, in fact, the matter will pass through the living state.
Yeah, you could use that angle. I'd be happier just saying the stars are alive right now, though. Especially a star. It's, the sunspots have always seemed to me. I wrote another novel called Frack and the Elixir, where the sunspots were living beings that live inside the stars. I got interested in that because that's an example of a living structured being that isn't based on DNA. There's actually, I even asked Robert Dawkins about this, and he didn't completely laugh in my face. So the idea is that you could have, because if you have, a sunspot is a vortex thread that goes from one spot on the sun to another. And they certainly have a huge amount of information in the complex vortex that they do. They can also split. They do give birth. They split into pairs. They eat each other. There's some sense in which they are a lot like living beings. But what we're not used to, we're kind of used to the idea of living beings that are based upon this digital model, this DNA model. And this would be a type of living being that didn't have a gene. So this would be a different kind of life.
You say that the memory is some excessive parts which is generated through the evolution, okay? The memory,
yes.
The memory is some irreversible productions,
yes,
and which cannot be eliminated, okay?
I think
you said that the life includes the memory and something like you say God and computation. Very difficult to pronounce for
this. Yeah, I'm not totally understanding. I'm sorry.
I'd like to ask you. You say that the history
yes.
and the time, the origin of the time and history.
Yes.
And I'd like to ask you, how do you think about the origin of the time? Was we are thinking that everything is evolved and that it is impossible to recover the past events. Okay. And you say that the memory is generated
yes.
Through the process of the synthesis between the my pronounce is very bad. Sorry, stages and stages. You mean that the synthesis, okay? And it's the essence of the origin. And through the process, you mean that the memory is generated.
Okay, I think if I follow what you're saying, I think maybe you're asking where the whole thing started, where the universe started. Would that be the question? Gee, I don't know. Maybe it's always been here. It's interesting about cosmology, how 15 years ago it was all nailed down, and we had the Big Bang, and that was it. And everybody agreed on that. And now the cosmologists have just gone bananas. It's only 5% of the matter, is it? Or 15% of the matter is real, and the other is dark matter and dark energy. Space is perhaps infinite. We're maybe in a hyperbolic space that has been infinite all along. And the Big Bang wasn't a point-like explosion. It was more like a hyperplane-like explosion at every point in space. It's nice to see that our ideas change so much. There's a tendency sometimes to think that things are done. One sort of technical consequence of the notion of hylozoism that I was mentioning, gave a talk in Osaka yesterday, that I think it's a safe bet that in 100 years we won't be using digital computers. We don't use watches with gears anymore. We tend to think, well, now we've got the digital computers and that's the end of the line. And I think it's pretty likely that we won't be using them in 100 years. And instead we'll be using probably biocomputers, or perhaps quantum computing will really come online. And if you get into quantum computing, really any object at all is a quantum computer. And you talk to it by shining light at it, and you get things out by looking at the light that comes back. And if this does come to pass, then the world might turn out to be a lot more hylozoic than we expected. It might be that you'll just take any object at all, and that will be the computer that you're using. Yeah, back there.
It was charming and wonderful talk. Can you hear me? There was another descendant of your, intellectual descendant of your great-grandfather who had some rather similar ideas. That was Friedrich Engels, who wrote an extraordinary book called The Dialectics of Nature, which I'm sure you'll know it. But of course, one of the things which he insisted on, which was part of his inheritance from Hegel, was that there's another rule which follows, which is the transformation of quantity into quality. And he would have said that if everything's alive, some things are actually rather more alive than others, and when you get to a certain level of life, you actually become a very different kind of life, and that you're going to have to define a different class of beings, which are actually the biota and living things which biologists will always be interested in. So I think, in a way, you're going to lead back to it as well as we think of it, even though it can go more dialectical route. I wanted to ask you another question, though, which is about the motivation for this. You say that that it's congenial, this idea that the universe is alive. I wonder, we've thought of a lot, good part of the world as being alive for a long time, including plants and animals and other human beings. It hasn't worked that well in terms of producing empathy and understanding and behaving well towards each other. You only have to go 200 or 300 miles down the coast from here to see what happened 50 years ago when the United States, who knew very well what they were doing to a part of the universe which was alive, but nonetheless killed 150,000 people in 10 minutes. I think that we need to have much more than just a sense of livingness to make us behave well, either towards other people or towards inanimate nature, but to the rest of nature. And I want to know what you actually buy with this congenial view that the rest of the world is alive.
Okay. Yeah, actually, well, first, the idea of the sliding scale of levels of life, that's an interesting thing. It's also, it's interesting to try to break that and be absolutist and say everything is equally alive. Because once you have a universal computation, in some sense they're all equally strong. But, well, if you believe in hylozoism, does that necessarily make you more likely to be good to the world? Well, I think I view it as a corrective. There's a tendency to downgrade the computational power of the world. You sometimes will see science fiction writers seriously, well, not seriously, propose the idea, why don't we disassemble Earth, turn it into a cloud of nanomachines, make this big hollow sphere around the sun so we can soak up all the energy, and then have the thing run a virtual reality simulation of us and the planet, and we'll all be immortal, and everything will be great. And to me, that seems like a really wrong-headed way of thinking, because, well, for reasons having to do with computer science, the fact that these gnarly computations that are all around us are irreducible, they're not things that you can capture the reality of with shortcuts. You don't want the kind of thing where there's a forest where every 10th tree is the same. It's sort of, I have a sort of dislike of virtual reality, the whole program of virtual reality, of saying that it's just as good as the real world. Because if you pay close attention to the real world, it's inconceivably rich and complex. And even the smallest thing is full of so much life and energy. Now, whether or not a real estate developer or a warmonger, or is going to be swayed by what an intellectual thinks is not very likely. Okay? So it's not so much that we can change the world. I think the more that I worry about changing the world, the less happy I am. It's very nice to be out of my own country and not to have to read about the evil fools who have been running America for the last 8 years. It's nice to be away from that and not to be under the heel of stupidity and greed. But if I think about that stuff, they win, because then I'm not living my life. I'm thinking about the politicians. I'm thinking about what they're trying to do. I am more and more attracted to the idea of, if I can become enlightened and be good to the people in my immediate circle, that's the most I can hope for. I can do what I can to change the world by writing, by having friends, by having family, by publishing. But I can't really base my life on wanting to change the behavior of powerful, evil people that I have no control over. And if I think about them continually, again, they win because they're sucking away my chance of enjoying my life.
Well, I think in your statement you use many words and which means philosophical way or so. For instance, being living or something, computation also. So in particular, well, in narrow sense of mathematics or physics or computational science, computation means to operate or manipulate a natural number. Finally, it's reduced to the in Turing sense that it's a manipulation of a natural number. Then, if you use this in such a narrow sense, then it causes a little problems in my opinion. But how you can, or do you use it in what sense? That computation in concept or something not related with an exact sense of the natural number or so. Could you please comment on
okay, yeah. You're coming back to the whole thesis of universal automatism, to say the world is made of computations. Because, as you say, usually we think of computation like an algorithm for adding two numbers or something for doing a computation. But if we think of it as a process that obeys finitely describable rules, and what begins to happen, if you do like a lot of physics simulations, you simulate balls bouncing around, and you begin to say, well, this is very much like a computation. I put this in here, and I get this out here. In fact, Toffoli developed something he called the billiard ball computer. He showed that you can take a computer and turn it into balls bouncing around. And in fact, the digital computers that we have are physical systems that are, the mathematics that we read onto them is actually kind of an afterthought. But the system itself, whether or not we looked at the mathematics, it's still doing a computation. So I'm using computation in a sort of loose sense here, because where I want to get is universal automatism. So I need to say that it's simply a process that obeys describable rules. And that's the burden of argument in my book, The Life Box, the Seashell, and the Soul, is to sort of work up the ladder. You know, physics isn't so hard, and then it's a little harder to get biology. It's a little harder to get human psychology, still harder to get society, harder to get philosophy. So it's a difficult thing. But it's, in principle, it's not an unreasonable notion.
Okay.
Thank you for very beautiful talk. Kind of reason. I like it. But one question. When you mention when you live, you're thinking every object is alive and present. By the time when you use the term hydrozoism. Why you use zoic instead of this?
Why do I use Hylozoic instead of what?
Yeah, your hydrozoism.
Yeah.
Then you use bios, and not bios, but zoic. Why you use?
Oh, well, that's the word that's in the dictionary. It's, if you look on Wikipedia, you can actually find Hylozoic or Hylozoism. And a related word is panpsychism. That's pan-psyche, and that's saying that everything has a mind, which is slightly different, because you could imagine having Hylozoism, everything was alive, but they don't have minds. And I think you could probably even get the opposite way. But it's, I like the word because it's a strange looking word. It's unusual looking, and it's good for the title of a book, especially a science fiction book.
Okay, so yeah, so when I worked on coupled map lattice, I had some feeling that I did not want to stop the simulation, did not want to kill the simulation, but I never thought it's alive. So, so I think, yeah, the living system has some kind of, so in the case of, so in the computer, so this memory and computation are separated, and the rule of computation and computation itself are separated, and that might not be true in the life system. Yeah. Yeah.
So you're saying it's hard to say living systems and computation because there's no separation between the rule and the action.
Yeah.
Well, there is again, I mean, in a physical computer, there's there's these electrons rushing around. In a way, they're sort of just as embodied. I don't think it's that different. I liked your talk, though. You kept going back and forth between, you say, well, let's try something, let's put luciferase on these bacteria, and then let's go and look at the computer model. I thought that was interesting that you're continually flipping back and forth between doing the simulation and the actual wet experiment. And so it seems that you, of all people, would support the idea that life is a computation.
Okay, but maybe we can continue the discussion at the dinner time. So, yeah, thank you very much for